Sort has a variant called QuickSelect, which can in fact do this. Okay? And QuickSelect looks very much like Quicksort, right? So, So if the partition is consists of only one element, then you're done. Okay? Otherwise, you divide that into two partitions, right? Just like Quicksort. Okay? Except that in Quicksort, you are interested in sorting the two halves and putting them together, right? In this case, you only want to find out the kth element. The kth element is either in the left partition or the right partition, right? So once you know which partition it is in, you only have to go down that partition, right? So the difference, therefore, is that QuickSelect, in Quicksort, you have to call the QuickSort on both halves, right, after partitioning. In QuickSelect, you call QuickSelect only on one of the halves. Okay? So, therefore, you end up with a recurrence relation so again, let's take the simple case. Let's say the splits are even, right? So then your recurrence will be T of n equals n plus T of n by 2. Again, partitioning is the exact same partitioning step that you use in Quicksort, right? You pick a pivot and then you put everything less than the pivot on the left partition, everything greater than the pivot on the right partition. Okay, so essentially what you're doing is you're guessing some element, right? And then saying, okay, let me see if that element happens to be the kth element, right? Well, it may happen to be, some j greater than k, in which case you are, right? So so you have n elements, right? So you pick some k randomly, right? And if that, I'm sorry. So there are n elements. So let's say you generate a j at random, right? And you pick that element, and now you do the partitioning, and everything below aj, and then everything above aj, right? So you generate a random number j, use aj as the pivot, and then you do the Quicksort partitioning, right? So now, if this position happens to be some I greater than k, okay? Again, you want the kth minimum, right? So if I greater than k, that means the desired element is in this half, right? Or I could be less than k, in which case the desired element is in this half. Okay, so depending upon that, you're either going to do QuickSelect on the left or right half, right? And let's say you're lucky and this I happens to be n by 2, then the recursive call is going to take T of n by 2 time, and then to do the partitioning, same Quicksort partitioning, which is linear time, right? So we have T of n equals n plus T of n by 2, and if you work out that recurrence, you will see that it basically turns out to be the summation n plus n by 2, right? So if you take T of n by 2 and apply the same expansion, it will give you n by 2 plus T of n by 4, right? So when you keep doing that, so you will end up with this sequence, which is a geometric progression, right? So if you take n out, then it's 1 plus half plus quarter plus, right? So that summation 1 plus half plus quarter, that ends up to 2, right? Sums up to 2, and therefore this whole thing is O of n, right? So QuickSelect, in the best case, is O of n, and you can try various other cases like, okay, what if I have a 10%, 90% split, and just as in the case of Quicksort, 10%, 90% split will still give you good asymptotic bound, which will still be linear. But the worst case is, of course, totally unbalanced. You have only one element in one partition and n minus one element in the other partition. Then you will see that that ends up being quadratic. Right? It's not even n log n, it is quadratic. So QuickSelect, if you happen to be extremely unlucky, then you will have a quadratic bound. But if, again, if you do some kind of a random partitioning, right? If you do, if you generate the pivot at random, then you have the average case or expected complexity that is linear. Okay. The question that comes up is, can we actually do better than just expected or average case linear time? Right? Can we do worst case linear time? Okay. And so there is in fact an algorithm for doing that. Okay. So this is an algorithm from 1973. So you can see that people had to use typewriters, right? So this is the list consists of very famous people, Ronald Rivest, from the CLRS book, Robert Tarjon, who's behind many graph algorithms that we use, Floyd of Floyd-Warshall graph algorithm, Von Pratt, well known for in programming languages, and Manuel Bloom.
Complexity.
Yeah, in complexity. And well, anyway, those are people from in the 60s and 70s. One of the things that you will see is that they end up, we specialize a lot more these days. In those days, you will see that people were able to work across many different areas. So we will look at, algorithms by all of them during this course. So the idea here is that if you spend a little bit more effort in how you pick, how you partition, and don't just use random or anything like that, then you can actually achieve worst case order of n complexity. Okay, so the basic idea, which I will mention now, and we'll discuss it in detail next lecture, is you first divide the set into 5 elements each. Okay, so n by 5 groups will be there. Now each group of 5 elements, you find the median. Okay, it's a 5, right? So you need to perform some 5 is a constant, right? So you need to perform only a constant number of comparisons to find the median. Okay, maybe 8, whatever, right? Some number, right? And now you have the medians of each of these n by 5 sets. Okay, and then among 5 elements.
Because there are constant elements.
I thought 5 sets.
No. For each set of 5 elements, you compute the median. Okay, and then after that, now you have all the medians. Now you apply the algorithm recursively on these medians. Okay, and if you do this, then you can actually prove that if you split on, if you use this algorithm, then you can prove that your splits will never be worse than 30%, 70%, and we know that from the previous picture that even a 10-90% split would still give us a linear time algorithm, right? So if you can get 30, 70, well, certainly we'll get linear time, and that's what this median of median algorithm for selection. Okay, so we'll continue the next lecture. Okay.